Welcome, everybody. It's my pleasure today to introduce Regina Rotman, and she'll be telling us about curvature and the length of a shortest periodic geodesic.
Okay, so should I begin?
Please do.
Okay. So let me first begin by stating the questions that are a motivation behind the works that I'm going to discuss. And there are two of those questions. First question was asked by Gromov, I think in 1983, which is, can you uniformly bound the length of the shortest periodic geodesic on a closed Riemannian manifold by volume? So specifically, is there a constant such that whatever Riemannian manifold we take, there will be a periodic geodesic of length bounded by this constant times the nth root of volume. So this is the first question. I know that this, this question, the hypothesis does not involve curvature. So one possibly can expect that this bound is curvature free. And then there is a similar question one can ask, and that be in terms of the diameter of a manifold. So is there a similar bound so that the length of the shortest periodic geodesic on M is bounded in terms of, this constant times the diameter of M. Okay, so in those questions are in full, those questions are only answered in dimension 2. So let me just briefly, then there is also a result in higher dimensions that I will mention, but let me begin with dimension 2 and let me, so for closed Riemannian surfaces, and let me right away say that it helps when the manifold is not simply connected. So for example, it is not hard to see that when M is not simply connected, the length of the shortest periodic geodesic is bounded by twice the diameter. So this is quite trivial. And then there were a bunch of results. So the first results were due to Lervner, and he established such a bound for A2 torus, for Riemannian 2 torus, and due to Pugh. Okay, so Pugh established a similar bound for a Riemannian RP2. And note that those bounds are sharp, and in general, we have bounds, but those bounds are not sharp necessarily. And then there were others. There were Akpola, Blatter, Yuri Borago, Zalga, and Zalgalia, Bavar, and Sakai. And in particular, Bavar has established the sharp bound for a Klein bottle, for Riemannian Klein bottle. Okay, so just to jumping briefly into higher dimensions, there is a result by Gromov where he for essential manifolds. So in case of essential manifolds, we also know that we can bound the length of the shortest closed geodesic in terms of the volume, the nth root of volume. Okay, and then we go to simply connected manifolds. And in terms of simply connected manifolds, well, if we go to dimension 2, then there is only sphere. And for Riemannian 2 sphere, well, first bounds were due to Croak, to Chris Croak. So his bounds were, the original bounds were 31 square root of area. Also 9 times the diameter. And then, so those were, he did not attempt to obtain sharp bounds. Those bounds are obviously not sharp. And they were kind of improved. So first they were improved to 4 diameters and 8 square root of area. And that was by Alex and myself, and independently by Stefan Saburu. And then the last bound I improved to 4 square root 2 square root of area. And those are not sharp bounds. One, in fact, expects that a sharp bound is obtained, well, one speculates this is a hypothesis due to Calabi, Croak, and Gromov. that it's 4th root of 12 square root of area, which is obtained by the following limiting case, where you take two equilateral triangles. So you take two copies, you identify them, glue them along their common boundary, and this will be your closed geodesic. Okay, and it is for a while we thought that we can always bound the length of a shortest closed geodesic by twice the diameter, no matter whether a manifold is not simply connected or simply connected. But there is a counterexample that's due to Florent Balashov, Chris Crook, and Misha Katz that says otherwise. So it's not a constructive example. Only thing we know is that the length of a shortest periodic geodesic can be greater than twice the diameter, but currently we don't know what to expect, like what should this sharp bound be. Okay, so now I'm going to go to, so failing to establish curvature-free results in general, we don't even know if it's true. I mean, maybe there are no curvature-free results at the moment. And maybe, you know, the counter examples is just cumbersome enough that we cannot compute much. So failing to do that, we try to use curvature. So in particular, in dimension 2, there is a relatively new result of Jan Adelstein, Franco Vargas Palette, that if you take a Riemannian 2 sphere, there is the length of a shortest closed, positively curved Riemannian 2 sphere is bounded by 3 times the diameter. Okay, and then there are a bunch of other results, some older results. For example, there is an older result of Alex and myself, and this is for a class of manifolds. This is for a class of manifolds, which we denote as M, D, K, V, and it consists of manifolds with sectional curvature. Bounded from below by possibly a negative constant, volume bounded from below. And diameter bounded from above. And together with Alex, we obtain that in this case, you can bound the length of the notation. Oops, what happened? Sorry.
Oh, no worries.
Okay, so this is weird. Okay, so is it okay? Everything's okay?
Yep. Yeah, we can see it again.
All right. So the length of, this is notation for the length of the shortest closed geodesic is bounded by a function of KVD. One can explicitly compute it. I just don't want to write it down at the moment. Then there are other result that I would like to mention is a result of a non-Wonji Feiju. Let me write it here. Sorry. And they show that one can obtain a bound for the shortest periodic geodesic, or shortest closed geodesic. I say periodic just to distinguish it from geodesic loops, such as for the class of 4-dimensional manifolds. With bounded Ricci curvature. So they found that there is a bound. Some function. Okay, so now the theorems that I would like to discuss are the following. So this is the first
Regina,
theorem.
let me interrupt really quickly if you don't mind going back a slide. And then on your tablet, are you able to I don't know if you see an image of me on your tablet, but are you able to slide that to the side just so that I
Oh, that's right. Oh yeah, here.
Oh, perfect.
Okay.
And then
Okay.
question in the old result, why should I expect this hypothesis on a lower bound on the volume?
Sorry, the lower bound for the volume. Oh, I see. Why do you expect? I'm sorry, I'm not sure I understand this question. But can we remove the lower volume? Is it correct?
Or why should I expect
So,
it's
yeah, that's right. So first of all, it quite possible that one can remove this assumption. But second maybe mention second thing that I would like to mention is whenever we have a some structural theorem for the class of manifolds, like Grover-Peterson theorem, okay, on finiteness of diffeomorphism types. Okay, we should expect that it is possible to get such a bound for the geodesic. I mean, this expectation is not that, well, we should not expect it otherwise. We don't know otherwise, there are no counterexamples. But that those structural theorems are helpful just to obtain it, okay? So in particular, the reason that it works out, okay, is that one can obtain the following result. So let me just I don't know whether, well, I'll say it right now, okay? One, so can I just postpone this answer, the answer in its full just to a little bit later when I discuss how we
completely.
Okay, yeah. Because it's going to just be more natural at that stage, okay?
Perfect, thanks.
Okay, so so the theorems that I would like to discuss are the following. This is the first theorem that I obtained recently, which was, after I placed it under the archive, improved by Rademacher. And so I'll actually discuss his proof. So improved. I mean, I think that my approach still has some value. I mean, his proof is easier, I have to say, and it improves it to the following. I think my approach has some value because probably can be generalized. I think it's likely it can be generalized to some limit spaces. So, but I will discuss his proof. And then there is another theorem that I would like to discuss. This is work in progress. So maybe, the theorem in quotation marks. So the first result, this is for positive Ricci curvature. And having been, after establishing for positive Ricci curvature, one can ask, can we generalize it to scalar curvature? And it so happens that we can generalize it in dimension 3. So this is a joint work with Evgeny Liokumovich and Maximo. Okay, so I'm going to first discuss Ricci bound. And as I'm discussing Ricci bound, I will also address your question. So the starting, first let me discuss the elements that go into improving the Ricci bound, right? So the starting point, and this is a starting point every time, is the existence theorem of Fiat and Lusternik. The state that on any closed Riemannian manifold, there exists at least one periodic geodesic. Maybe let me provide a brief proof of this theorem, okay? So the proof is by Morse theory on the space of closed curves. This is all piecewise differentiable closed curves on M. And that allows us, and from homotopy theory, we know that there exists Q such that the Q's homotopy group of M is trivial. And but Q minus first is not trivial. I'm saying something, sorry, but so Q minus first homotopy group of M is trivial. I'm saying something silly here. But of the, I don't need -1. Sorry. But of the, that's right, of the loop space is not trivial. That's correct. And so we're going to consider the loop space. And here is M that sits inside there because we can identify M with a constant path. And we're going to consider a non-contractible sphere in the loop space. Not contractible. Okay, so here it is. Maybe. And we are going to try and deform the sphere to M along the integral curves of the energy functional. And we know that we cannot deform it to M because this sphere will be contractible in M. Okay, and so we should not be able to do that. And so what's going to prevent us from deforming it to M? Well, there should be a critical point of the energy functional that sits below. And this critical point is a periodic geodesic. And so let me now mention that if we are successful in, each point here on the sphere, right, is a closed curve. So if we can actually provide a bound on the length of those short curves, then that will give us an upper bound for the periodic geodesic. So the idea is somehow either to establish a periodic geodesic by some other means or come up with a sphere that's made out. So a sphere that's not contractible in the loop space that's made out of short curves. And here is what we note. We notice, this is some argument that maybe I will deliver later, that if we can contract loops, then we can come up with such a sphere. So we can contract loops in a nice way. So by contracting loops, I mean the following. Then that will lead to this this map. This, then we can take some homotopy class and represent it by a homotopy class that passes through short loops. And by contracting loops, I mean the following. So we take a curve, we fix a point. We want this point to stay fixed. And then there is a homotopy to a point through short loops. And so at some point you have asked, well, so why is this, why are those conditions on curvature, volume, and diameter help? Is because in this situation, we can effectively contract loops. And then the question is, can we drop, for example, the assumption on volume? Maybe. I mean, I've tried to figure it out for a long time. I was not successful, but it could be that it's possible. Okay, so hopefully that answers your question. So this is why Ricci, lower Ricci bound helps. Okay, so let me, because there is a Banner-Myers theorem. So Banner-Myers theorem implies that when we have Ricci greater than or equal to n-1, well, first of all, it implies that the diameter is bounded by pi, as we know. But also, if we look at the Banner-Myers theorem closely, it implies that whenever we have a long geodesic, we can nicely shorten it to the length of shorter than pi, right? I mean, so whenever we have a long enough geodesic, and that in particular applies to geodesic loops. Okay, so every geodesic loop of length greater than pi has index greater than or equal to 1. Now, also, and this is what already Martha noticed, that if we have a geodesic loop of length greater than I pi, has index greater than or equal to I. Okay, so so here's what we can do, right? I mean, we can let us consider a space of base point loops. So those are all the piecewise differentiable curves with fixed point P, closed curves. Based at P. Oops, something happened. Just a second. Okay, so let us consider any sphere. Okay, and let us consider the energy functional. And let us assume for a second that it's Morse, it doesn't have to be. Okay, so we are going to try, so I'm going to now make the same picture. I'm going to now assume that this is a base point loop space. So I'm gonna now try and deform a sphere, any sphere whatsoever, until it is stuck on a critical point. Okay, so here is a sphere in the loop space, and now it hangs on a critical point. Okay, so you know, this is a geodesic loop. Okay, and this geodesic loop will have index at most, so the sphere of dimension q, the geodesic loop is going to have index of at most q. And therefore, because it has index of at most q, all those curves here, well, all those curves hang below this critical points, all the curves, and this gotta be short by the argument of already marker. So all the curves here are gonna be short. And so you can use this sphere to bound the length of a geodesic, of the shortest geodesic. It's gonna do it to any sphere. And yes, the I mean, the energy functional doesn't have to be Morse, but if we take a point P, it will have a neighborhood, okay, such that if we look at the path, so it will have a point X here in the neighborhood, such if we look at the path space here, the energy function is going to be Morse, and so we can modify this argument a little bit and we'll be fine. So let me now go to the result that I would like to discuss. And this is our work in progress with Liokumovich and Maximo. Okay, so first so I'm going to discuss some elements again that go into the proof. And then I'm going to discuss, well, the trick actually on which this proof is based. So first, this first element is a result by Liokumovich and Maximo. There exists, and this is there exists a Morse function. So we are dealing right now with a three sphere with a positive scalar curvature. Now, the results that we are proving will be true for other manifolds as well, but actually it's going to be easier if it's not a three sphere. So three spheres is I think I would say is the only interesting case. Okay, so if we have a three sphere, Liokumovich and Maximo have showed that one can foliate it by two spheres, which with relatively nice geometry. Okay, so in fact, we will have something like this. So one can foliate it by spheres like this. Something like this. Okay, so what we can say about those spheres, right? And we can say that the area is going to be bounded in terms of the lower bound on the scalar curvature, and the extrinsic diameter, the diameter in the outer, the outer diameter is going to be also bounded. Okay, and so it's foliated, as I said, is going to be foliated by two spheres. Now, this is the first element. There is another element which says the following. So let's say we have a Riemannian 2 disk. Okay, then one can. So we have a Riemannian 2 disk, and we know the length of the boundary of this Riemannian 2 disk, and we know its area, and we know its diameter. Then it is possible to construct loops here. And the length of loops is going to be controlled in terms of those parameters. This is not as, should I say, trivial as one can possibly think, because if you drop by the area and diameter, or diameter, it's going to be not true. Okay. So one of the, so you cannot purely control it in terms of, in particular, in terms of the area. And this Frankel and Katz provided a series of counterexamples to that. And the fact that you cannot control it just simply in terms of area is rather simple. So this is Frankel and Misha Katz. I mean, one can imagine that one has something like this. Sort of, you know, a disk with those very thin but long fingers. And then, of course, it will become difficult to construct the boundary without increasing the length of the loop proportional to the diameter of the disk. But if we have both control of the diameter and the area, then we can construct loops. And so, in particular, we hope that this applies to this two spheres by which Liokumovich and Maximo foliate this manifold. In fact, there is an ingredient missing here, because this is the bounded diameter, but not the intrinsic diameter, and we need to bound intrinsic diameter. There is this idea that it seems to be working out, that well, one can exchange the extrinsic diameter for the intrinsic diameter by increasing the number of connected components, and we will not care about the number of connected components. It doesn't matter to us. So now let me just go a little bit. I think I have about 5-6 minutes to go a little bit into the details of the proof. And it's actually, so how do we use those two things together? So remember, we would like to be able to, construct a map into the space of closed curves that passes through short curves. And in this case, the map that we will be constructing is this. And in fact, it's going to look something like this. So we're going to have this disk, but its boundary is going to be sitting in M. Sorry. And it's going to pass through short curves. So actually what we want, in effect, is to take those spheres which foliate this manifold and partition those spheres continuously into short curves. So I'd like to partition them continuously in the short curves in such a way that this is going to be a sweep out of a Riemannian 3 sphere with which is our space. So I'm going to describe how we are going to accomplish this. So let me erase whatever I have here for now. And it relies on a kind of like the basis is a rather simple observation. The observation is the following. So let's say we begin with, okay, let's say we have a diagon. I mean, there is a simple lemma from the from topology, right? That if we can take this, so let's have this diagon connecting 2 points. We know that if we can construct this as a loop, if we look at this as a loop based at P, and we can construct this loop to a point, then there is a homotopy between E1 and E2 over path. There is path homotopy, right? I mean, this path homotopy will look something like this. So we start with E1, we slowly grow out E2, and then we construct this loop. And at the end, we are going to be left with E2. Well, I mean, one can make it effective, okay? So in fact, if we know lengths of E1, lengths of E2, and if we know the lengths of loops over which we construct this, then the curves in this path homotopy, their lengths, well, the curves will look something like this, and the length is going to be controlled as well. And so, well, I mean, so this is a series of pictures that demonstrates what I just said. So let's now try and apply this to our situation. So I would like to change. So remember, I'm starting with a sphere. Let me start with a sphere that's first that's swept out in a specific way by curves that potentially are long curves. And I would like to change those curves, right? So this is a map into space of curves of an interval, which begins and ends with a point, so it's easy to make it into a map of a circle. I would like to replace it by a homotopic map that passes through short curves. So here is the first step. Okay, so I'm going to look at an arbitrary curve, and I'm going to just draw it as if it is unlooped, but keeping in mind that this is the same point. So the first step that I'm going to do is I'm going to try to take this point and continuously connect the points on the curve by short curves with P, continuously connected. So the natural way is try and connect it by geodesics. But if I try and connect it with geodesics continuously, I will not succeed. I mean, there will be, it's possible that this curve passes through the cut locus and there might be geodesic diagonals that will result in discontinuity. So the question is, how do we, what do we do with this geodesic diagon? So I'm sorry, I'm now a little bit over the time, but I'm going to take a little bit of time just to finish, okay?
So please do, yep.
Yeah, so there will be those geodesic diagons, and I would like to fill those geodesic diagons so that there is no discontinuity anymore. So in order to fill those geodesic diagons, I will use the following fact. I'm an O2 sphere. Together with Evgeny and Alex, we have shortened that on those two spheres, the loops, and if we know the area and the diameter of the two sphere, those loops, if we look at this diagon as a loop, they can be contracted over short loops. Now, if I remember, this little observation, that implies that I can pass from, I can pass from one curve to another curve through short curves. So this allows me to fill this geodesic diagon. And so I obtain a family of curves. That continuously connect P with points on this curve. Okay. So now let me explain how I'm going to change the curves on a sphere to some other curves. Okay, so I have this. I have a map to the loop space. So I have this unit interval. And for each point here, I have a curve, I have a loop, right? I mean, each point here corresponds to a loop. So I'm going to first subdivide this interval so that neighboring loops are within distance epsilon from each other. So this here, those are the images of the points of subdivision. And those loops are close to each other. Okay, so I'm going to now look at, so this is T sub I, and this is T sub I plus 1. And let's say this is alpha T sub I, and this is alpha T sub I plus 1. I'm going to draw them separately. So here they are. And remember, I can construct a family of curves. So if I take this point, I can construct a family of curves that continuously connect this point with points on the curves. So for each of those guys, I have something like this. In fact, it's not obvious from this picture, but this last curve is going to be a point. So I'm going to replace, what I'm going to do is I'm going to replace, so I have a curves between alpha T sub I and alpha T sub I plus 1. I'm going to replace those curves by something else. I'm going to replace them by the following loop. So first, let me note that if I take this blue curve right here, maybe I'll do it as a color purple curve. If I take this curve right here, I can contract it to this point right here over short loops, because I know the length of each of those blue curves and I can connect them by cutting across. Okay, something bad is happening again. Sorry. Okay, so I'm back and I would like to move your picture. Okay, here, right? I mean, so if I consider this purple loop, I can contract it to a point like this. And because I can contract it to a point like this, there will be a natural homotopy between this guy and this guy over short path. Okay. So I am replacing, in fact, those black curves by something that looks like this. So in this case, it's just going to be a family of growing loops. They're going to grow and then I grow back to the point. So so those is going to be a piece on the homotopy because I'm going to do it to all the loops in the I'm going to do it to all the curves in subdivision. So why are those two maps? The resulting map is going to, and this is going to be through short curves. Those are going to be short. So why is this last thing I'm going to say, and I'm going to stop. Why as a homotopic is because we don't have to replace everything right away. We can replace continuously. So first we can begin by, instead of replacing those curves by points right away, we can replace them by something like this. Just keep the part of the curve and replace the other ones by those loops right here. Okay, I think, maybe this is a time I'm going to stop.
Great, thanks so much. So before we get to questions, let's briefly unmute ourselves and applaud. So now let's move to questions. What questions do we have? So Regina, let me start. So this last argument you were making is sort of how you can do this all continuously in a homotopy. And the point is that, I mean, in your first drawing, the purple loop was all the way on the outside, but you're saying you could just start with the, very small and then drag it to the right. Did I get that correctly at the very end?
I am not sure I understand your question. I'm going to try and understand your question. Okay, so drag it to the right. I don't necessarily understand what dragging it to the right.
The picture you drew on the bottom where,
okay.
Right.
So I'm saying this, right? I mean, so, okay, I'm going to try and say it better because I understand that I said it maybe not optimally. So I would like to replace all those. Okay, so first of all, let me say it like this. I would like to replace all the black curves that I have at the top and all the curves that I have not drawn that are in between them. Okay, so I would like them. I would like them to replace by short curves, and which this is my my little doodle that symbolizes those short curves, and I would like them. So eventually, I would like to obtain a map here. Let me call it F tilde that's homotopic to F. And so the idea is that I'm going to replace them by those purple auxiliary curves that I have constructed before, because I know the short loops are contractible. And the bottom picture says that this replacement can be done not like at once, like I've described, but continuously, where I don't replace all the curves at once, but I replace only parts of the black curves. And so as I replace them, and this is, I guess, what you mean by dragging to the right, right? I mean, they replace more and more of a black curve. As I replace more and more of the black curve, eventually I will end up with a picture like this. Did I answer your question?
Yeah, thanks so much. Further questions? I'll jump in with another question. So you explained in these results about you have a disk and a manifold, and if you have bounds on both the diameter and the area, then you can contract that disk through loops that don't get too long. And you sort of explained how both the assumptions on area and diameter are necessary. So the picture you drew was a picture where the showing that the diameter bound was
Right.
necessary. What's the picture I should have in mind showing that the area bound is
Yes, but
necessary?
that's a little bit more difficult. In fact,
I see.
Yes, I'm going to describe it. So Frankel and Katz answered this. Let me draw this picture, right? I mean, so this is a series of examples by Frankel and Katz. Let's just we start with a disk, and let's say we place in this disk a tree, and let's imagine that along this tree we build a wall. Or maybe you can imagine that you along those tree, right? I mean, and the result will get progressively more complicated as the height of the tree increases. Okay, let's pretend that you kind of took a finger and just made an indentation. Okay, so let's say we are trying to contract the boundary of this disk. Okay, so there is this combinatorial argument that will have to, as you contract it to a point, you will eventually have to pass through many branches of this tree, like a log of the number of the height or something. Okay, so and as you pass through those branches, your curve inevitably will have to get longer. Does it make sense?
And what tree was this again? How was this tree chosen?
Okay, so I have to choose this tree so that the edges are not I have to choose this tree carefully so that the tree doesn't make it easy to go around the tree, and so that it does not increase the diameter.
I see.
But other than that, it doesn't matter, right? I mean, as the height of the tree grows, I deleted part of my picture. Right, as a part of the tree grows, you will have to pass through more and more branches, and so your curve will kind of start hanging down. And as it hangs down, right, I mean, the length is going to increase, and it's going to increase proportionally to the height of the tree, and not proportionally really to the diameter. Okay.
Great, thanks. Yeah, I get the basic idea.
Mm-hmm.
Further questions for Regina? Well, if not, thanks so much for a wonderful talk, and let's stop the recording here.